In this video, I'll discuss about what is regression analysis. This will be an introductory session. This will be followed by more rigorous analysis on regression analysis, and that will be in a detailed fashion. And we'll also have a hands-on session using SAS. Those things will be in subsequent videos. This video is fairly simple. I'll keep it very simple for those who are getting introduced to regression analysis. Well, regression analysis is basically used to predict something by using something else, or you have information on one particular event. Using that event, you want to predict some other event. Okay, so in terms of variables, so you predict the value of one particular variable based on the value of at least one independent variable or one variable. Okay, so what is independent variable? You'll come to know that. So say for example, you want to predict whether it's going to rain today or not. Okay, so you have the humidity data for the last 4 hours. So based on the humidity data that you have, you want to predict whether it's going to rain in the next 2-3 hours or not. Okay, so you have data for couple of days data, and based on the data you have seen that okay, at one level of humidity it actually rains. Okay, and then there must be a pattern between the humidity content in the atmosphere and it's actually raining. Okay, so there must be some pattern. So we just want to find that pattern by using regression analysis. So that pattern is nothing but a linear equations. It's like rain equal to one constant value plus another constant into your humidity content. It's like a linear equations, like y is equal to 2 plus 3 into x. So if you have a value of x, you will always be able to find out what is the value of y, right? So all we need to know is the value of x, and then we can use this formula to find out what is the value of y. Similarly, in regression analysis, we'll have an equation using which we'll find the y value. We already have the x value in place. Okay, but we need to know two very important things. One, the intercept and the slope. So in an equation, y is equal to 2 plus 3x. 2 is our intercept and 3 is our slope coefficient, right? So regression also helps finding out the impact of change in one variable, or the variable for which we have the information on the other variable. Okay, so let me start you by telling what is an independent and dependent variable. Like I gave you an example, right? Y is equal to 2 plus 3x. So x is our independent variable, y is our dependent variable. Y depends on x, hence y is the dependent variable. X doesn't depend on y. It really causes y. So x is the independent variable. Okay, so using regression analysis, we can get to know if there is a change in x, what is the corresponding change that will happen in y. So in our example, if there is a change in humidity, how much more rain is going to happen, or what is the chances that it's going to rain? What is the change in the chances, or what is the change in the quantity of rain that is going to happen? So that kind of a relationship we can get to know. So we'll start with simple linear regression model. So what is a simple linear regression model? First thing is, what is simple? The word simple is used in which we have only one independent variable. Like I said in the beginning, we can have as many independent variables as we wish to have, but if the equation has just one independent variable, we call it a simple regression model. Why it is a linear? Because the coefficients, whether it is slope coefficients or the intercept, are linear in nature, or they are not, curvilinear or quadratic, that kind of a thing. It does not be cubic or quadratic or logarithmic in nature. Okay, so the relationship between x, y essentially should be in a straight line fashion. Okay, it should not be parabolic, circular, that sort of a relationship. Okay, or maybe you might have heard about linear functions, like fx is equal to x plus 3. So this is a linear function, but fx is equal to or f of x is equal to x square plus 2. So the relationship between fx and x is not linear, it's actually non-linear in nature, right? So in linear regression, we should have a linear relationship or linear function. The regression equation that we get at the final stage of the modeling process, it has to be linear in nature. We'll see that when we do the hands-on exercises. So type of regression models, you have the positive linear relationship, very straight line. So as I said, a regression line is something that shows the relationship between two variables. You have x and you have y, right? So you have different data points. So what does regression does? It does one thing. It helps you drawing a line in between the data points. Okay, for each value of x, you have a corresponding value of y, right? So what really best represents the relationship between x and y? A straight line that passes through these data points. So how do we draw this straight line? Well, that is the core thing that we are going to study. We call it as ordinary least square regression. We'll study that. So that is one mechanism using which we draw this straight line. So our straight line could be indirect as well, or it could be downward sloping as well. In this case, you have a negative linear relationship, right? And when your data points are all parallel to the x-axis, you can have a very straightforward regression line. So that means there is no relationship between x and y. There is no point in doing a regression. When there is a non-linear relationship or a curvilinear relationship, you will have the regression line to be some kind of a curve. Okay, it's not a straight line, right? As you can see. I have already mentioned this. Linear regression look like this. You have a y, which is dependent variable. So this is the variable of interest. We don't know this. Okay. So we have the data. When we do it empirically, we will have the data for historical period, but we want to predict this for future, but we don't know this at this moment. X is our independent variables. So this is a variable for which we already have the data in place. Using this, we'll get to know what is going to be y. Okay. So you have beta naught. So beta naught is nothing but the slope, the intercept, beta 1, which is the slope, and then we have an error term. So what is an error term? We'll just see that later. Okay. So we have an error term, and we all call it random error because it keeps on changing with each and every data point. Okay. We call this equation a population linear regression. Why population? Because we deal with the population data. Okay, the whole data, and there is something called sample data. We sample it. It's not always possible to take the entire population and do the modeling. So most of the cases will be only having the sample data. Okay. And in sample data we do the estimation. Okay. So we expect that our sample linear regression is close to our population linear regression. Well, the best thing is obviously the population regression, but then we hardly have situation where you will have the access to the entire population data. So most of the cases we go in for the sample data. Um, so there are certain number of assumptions that is there in linear regression. The error value or the random error should be statistically independent. That means the corresponding error values should not be correlated. Okay, you can check it very easily. Just by doing some statistical test, we'll come to that. So that is one assumption. The error values should be normally distributed. Okay. Again, you can check it by plotting the error, or you may wish to have some statistical test. You can do that just to see that whether your errors are normally distributed or not. And then the relationship between x and y should be linear in nature. That means all you can do in linear regression is that you can plot a straight line. You cannot have a regression line that is curvilinear in nature, or it's a curve. You cannot have it. So make sure that you have a linear relationship in place between x and y. So this is an example wherein you have these 6 data points lying in different places. So by doing just a guesswork also, we can plot a line inside that passes through the middle of these points, right? But we can always have this line better by using an algorithm which we call it as OLS algorithm. We'll see that later. Here as you can see, the difference between this line or the regression line and the actual data point is known as the error. Okay. All we are trying here is that generalizing the relationship between x and y. Okay. So we are saying that the perfect relationship cannot be established, but there is some relationship which is very close. Okay. So the line says that the relationship between x and y is best established by this line. Okay. Or we can get to know the relationship between x and y by looking at the line. It may not be 100% correct, because you see one point here, one point there, again coming down. So there is slightly a deviation, but then that deviation is captured in the error part. Okay. So this is the error, difference between the actual point and the point on the regression line. Okay. So the idea is that you have a positive error here, right? So for this particular point you have a positive error. For the next particular point you have a negative error. So the assumption is that this error should cancel out. Okay, so there is a positive error here, there is a negative error here, again there is a positive error, again there is a negative error. So if you take sum of all these errors, if you add these errors, it should be close to 0. That means the final error should be very minimum, or it should be very minimum. So that is the intention. We should have a straight line in such a way that the random errors, when we sum it, it should be very minimum. Okay, so that's the point. So what is this intercept? So intercept is nothing but the distance between your origin and then the point where your regression line cuts the y-axis. So that's the intercept. So what is the slope? Well, slope is nothing but you take any point and then draw a parallel line with respect to x and draw a parallel line with respect to y. Okay, and this is the perpendicular and this is the base, right? So perpendicular by base is nothing but your slope. Okay, or maybe if you want to compute the slope in some other way, you can just measure this angle between your regression line and the base and take its tan value. So tan of that angle will give you the slope. So what the slope tells us, slope also tells us about the relationship between x and y. Okay, if the slope is less, the relationship between x and y is not that strong. But if slope is very high, then the relationship is quite strong. So that's how we interpret the regression line. So this is the population regression line. We'll come to the sample regression line as well. Well, sample regression line is nothing but the estimated regression line or regression model. Okay, the notations are a bit different, but the concept is pretty much same. So we instead of using y, we use it y hat. Why hat? Because we predict the value, right? These values of y in the sample regression are predicted, not given a priori. Okay, using the sample data, you predict the values, right? So these values are not the actual values. You can always compare the actual values and the predicted value, obviously, but y hat is used to represent the estimated value or the predicted value. Okay, and then b0 is your intercept and b1 is your slope coefficient. Okay, why is there no random error? Because you have already estimated it, and in estimated equation the assumption is that the sum of the error components should cancel each other and should be 0. So in the estimated model we never have error in place. One of the assumption is that sum of the error should be 0. Okay, so we go by that assumption and we don't keep error term in the equation. I was talking about the least square criteria or the OLS regression, ordinary least square regressions. So how do we compute these equations? We compute by the compute from the the following way we compute. So what we do is that we compute the error value first. Okay, so y is our actual data and y hat is our estimated data. Okay, so we compute the square of the error of that and we take the summation. Why do we take the square? Why just we can take the error as it is? Why we square it? Because if you take the summation, it will become 0, so you won't have anything left. So we just square it for mathematical purpose. I mean we square it to ensure that the algorithm can be run in a way, and it's not going to cause any issue. If you don't square it, it's going to be very problematic. It's going to be very problematic while doing the estimation. Okay, so the criteria is that the sum of the squares should be minimized. I was talking about that, right? We should draw the line in such a way that the square of that distance between the regression line and the actual point should be very minimum. Or essentially what we are trying to do is that the line should be very close to the points, so that the line represents the pattern in the data. Okay, so that's the criteria. So we do the minimization. Okay, we use the differential calculus to find out the intercept and the slope coefficient. So y and x both are given to us. We have the sum of error square. All we need to know is beta naught and b naught and b1, and we can find it out by using differential calculus. So by using differential calculus and doing some sort of mathematical steps, we can arrive at these formulas. So the formula to compute beta b1 is the following. We can see it on the screen. and also you can compute your intercept once you are done with computing with your slope coefficient. Okay, so you can use these two formulae to actually find out the slope as well as the intercept, and once you have that, you have the model in place, so you can put it. So finally we have an equation, linear equation, that shows relationship between x and y. So say for example your beta naught is 0.5 and your beta 1 is 0.8, and you are trying to find out the relationship between x and y. So finally your equation will be y is equal to 0.2 plus 0.8 into x. So if your x is 2, so what is going to be your y? Your y is going to be 0.2 plus 0.8 into 2. So in place of x you put 2, right? So 1.6 plus 0.2, so that's 1.8. So your y value is 1.8. Okay, so that's how you have built the model, and you can use it for a variety of purposes. So how do we interpret the slope and intercept? In fact, this is very important. When x is 0, that means there is no x. Your slope coefficient is going to be 0, because slope coefficient into your x, which is 0, becomes 0, right? So your model has only this slope. So your only the intercept. So your intercept tells you that when x takes 0 value, or there is no x, what is going to be your value of y? There is no x. X is completely null. So what is the value of y? That is nothing but equal to the intercept. Okay. So how do you interpret a beta 1 or b1, which is the slope coefficient? When you change x by just 1 unit, like I said, no, x was 2 previously in the last example. Okay, and now I make it 3. So when I make it 3, y takes the value of 2.8. When x was 2, the value of y is 2.6 in fact. Okay, like 0.2 plus 3 into 0.8 into 3, right? So it is 2.6. So what is the difference between 2.6 and 1.8? It's 0.8. That means when you increase x by 1 unit, what is the corresponding increase in the y value? That is nothing but your slope coefficient. So if you increase x by 1 unit, y will go up by 0.8 unit. That is the explanation for the slope coefficient. So how do we compute the coefficient using the different statistical tool? Well, you can directly use programs which will compute it for you, but it is always recommended that you do it by yourself sometimes, just to get a better understanding. Obviously we have software who will do it for us. We don't need to worry about how do we use differential calculus to compute beta 1 and beta naught. It will always be given once we run the program, but it's always good to have some understanding. Okay, so let's take an example here and do it using Excel. So you have house price and then square foot. Okay, like the area of the houses. Okay, so that's in the square feet. So y is your house price, and x is your square feet area. So we want to know how y depends on x, or how price is dependent on the area of the house. Okay. Now in Excel we have the statistical package where we can use the analysis tool pack to find out regression. Then we have house price in one column and then area in another column. We select y and x and we press OK, and we'll get the regression output. In the regression output, as you can see, yes, 1 second, I will just adjust this slide. Okay, it's not happening. Okay. Anyway, so we'll get into the other things later. Just look at the intercept value. It's 98.24, and then the slope coefficient, that is against the square feet, right? 0.110977. Okay, so this is our beta naught, the B1, sorry, B0, and this is B1. Okay, so we have our intercept as well as the slope coefficient given to us. Okay, there are other things also. We will also study what is R square. Okay, what is T statistics, what is P statistics, what is confidence level, lower confidence level, upper confidence level. So these things are covered in the hypothetical testing video, and also we'll study the detail about linear regressions in another video. This is the basic one. Okay, so what will be our linear regression? So house price is nothing but 98.24 plus 0.10977 into square feet. So this is a simple linear equations. So if we have square feet in place or the area in place, we can just put it there and then compute what is going to be the house price. Okay, so when we plot this, we find this out. So this equation, when we plot it, we have the regression line in place. Okay. Well, there are some more properties. As I said, the sum of the residuals should be equal to 0. Okay. And there is another property about the regression line. The regression line always passes to the mean of the y variable and the mean of the x variable. That means it passes to the mean. Okay. It passes to entirely in the middle of the observation most of the time. Okay. And then there are more technical properties. We'll see that later. Once we study what is unbiasedness, what is biasedness, what is R square, what is hypothesis testing, what is significance, insignificance. So all these concepts will be covered in another video, which will have a detailed detailed analysis or detailed overview of the linear regression, and then we'll also go on to study multiple regression, which will have multiple independent variables, which is obviously of higher complexity. So for now, we'll stop it here.